researcher and a lecturer at the Hebrew University in Jerusalem in computer science. He also has a job or affiliation with a company named Eyeway Vision that's connected to artificial reality?
Augmented reality.
Augmented reality, right. The A. Dr. Shovman will talk about the end product, the audience's comprehension of visualization, and the talk will touch on both the theoretical and empirical aspects of how people understand visualizations. So, Mark, go ahead.
Thanks. Actually, can I take this? I'll walk around. Thanks. Well, actually, taking the stage after Barbara is a bit daunting, but what I'll be talking about is my PhD project, because there was lots of things done at the kind of pool. That was done in the University of Upper Dundee, which you've never heard of. But you have heard of one guy from Dundee, I'm sure, William Playfair. You've heard his name several times already. The guy who, first of all, single-handedly invented most of the visualization formats we use today. And also, and the interesting thing, he had to spend a lot of time and effort to proselytize, to convince people to use these formats. It wasn't easy. I mean, it took some time and effort on his behalf to sell the format, the pie charts and bar charts and things you can see in Calculist every day. And that was 200 and a bit years ago. And since then things changed a bit. There's more data. There's much more data in all dimensions. There's more dimensions, there's more data, there's more types, there's more everything. There's less time to analyze and draw conclusions from the data and less tolerance for wrong decisions. In many cases you need to do it now. And the old tried and true formats don't cut it anymore. They're not good enough. And the new ones are not there yet. Not all of them. Some new formats are good, but it would be nice to have another 200 years to polish and have a natural selection of what's the good, the perfect format for the data we have now. But we don't have 200 years, and it would be really even better to have kind of a black box test that you can design a new visualization format, show it, and say, okay, that's a good one, that's a bad one. Okay, that would be nice, right? Yeah. So that was the kind of golden goal, and towards that goal, from my background in cognitive psychology, started thinking about what would be the criteria of efficiency of a visualization. Now, I don't know what the novel format is. I want to be able to check, given a new chart, is it good, is it bad? Okay? So any criterion that I would have to devise would have to be relevant and generalizable across domains, so it's not domain specific. Okay? To make things simpler, I wanted to focus on a visualization technique, not a tool, not a big thing, small thing, like a bar chart or something of that kind of complexity, and focus on insight, not on. And that's an important bit, because visualizations are used for communication, comprehension, conviction, deception, learning, what have you. I was focusing specifically on insight, on exploratory visualization, where you don't know the answer, you have the data, you visualize it, you're trying to understand what's going on in there. And that's your criterion. Did you understand what's going on in there from the visualization? Okay? That's the many questions, that's the question. So if we're taking a representation of visualization loop, we have some world, a phenomenon that's measured, data is visualized, chart is perceived in a kind of proper way, and that information that is affected by both goals and expertise leads to decision and action on the world. Then what I'm interested in is the information, is the insight about the world. Not about the chart, about the world. Okay? And the first empirical study was me, in my first year of PhD, running after all the researchers that didn't run faster than me in the University of Upper Dundee, and interviewing them about their research that involved any kind of visualization. Okay? It was reasonably semi-structured interviews. I asked them questions, pointed questions about what kind of research they did recently that involved some kind of breakthrough or insight that involved visualization, any kind of visualization, and then asked them to sketch me the visualization that was, key plot, and talk me through it. Okay? And what they talked about was, of course, their subject domain, which ranged from criminology to river studies and what have you, and psychology and mathematics and whatever. And while they were talking about their domain, I was listening about the chart. What chart elements, what visual elements were the key ones that led to insights, okay, the domain insights. And I called them visual insights or visual correlates of insight. And in this example, I don't know, can you see that? That's a hydrologist. That's the riverbed. It's an actual scan from the interview proceedings. So it's in the riverbed. She was talking about how the measurements didn't add up, and I saw, okay, that's an important point. She was pointing about that one. That's an outlier. And actually, when I was trying to afterwards to do another pass and see what the visual correlates of insight were, what were the visual elements? They were mostly outliers. Mostly people used visualizations to detect outliers, mostly as an 85%. Yeah. Then were clustering data into and seeing how it divides, and then seeing trends, and then maybe, I'm not sure about those enough data, recurring patterns. I'm not sure it's different from trends. Seeing some sort of recurring patterns. So if that's our chart, for example, that will be the outliers. There are two trends, two clusters, and this is linear trend, and that's the non-linear trend. Okay, that's kind of thing that, from what I saw, people use visualization for. Okay, so a criterion, coming back, for a good visualization, that is, if it allows these kinds of insights. Basically, if it allows outlier detection, efficient outlier detection, we're covered for 85% of cases. Okay, it's good enough. If it allows all of these in an efficient, easy, fast way, we're reasonably covered. Okay, so that was one step towards a criterion. Right, now, how does it work? Okay, can we build something like a cognitive theory of visualization comprehension? In fact, I'm not sure we can, but people try, but I don't think we need to. Because charts are a recent phenomenon, I mean, even if we're counting from the cave paintings, it's recent from the evolutionary point of view. So there cannot be a specific cognitive model. There's not a part of brain that evolved to perceive charts. Okay? There is a part of brain that evolved to perceive faces. So everything that is visualization comprehension, everything that's chart perception, anything that is, as well as reading actually, rides on top of existing brain structures, existing cognitive structures. We don't have to invent a new theory. We can actually look at what has been done on visual perception and comprehension and all that, and somehow kind of pick and mix existing theories to see what is applicable, what does make sense for charts. Okay? And the main thing, because charts are kind of in between natural scenes and abstract things, it's something that between existing theories of natural scene processing, natural vision, there are tons of that, and reading comprehension, and there's tons of that. Something between these we can mix and match, I hope, something that would explain what happens in your mind when you see a chart. Okay. And the first theory that went into the mix is not the laws of Gestalt, but the principles of perceptual organization, which is the modern version of the laws of Gestalt. We all know and love the laws of Gestalt. And they've been around for 103 years. This year, everyone knows about them. They're very convincing imagery. The images are very kind of shiny. I don't know. But it's been superseded since then by newer, more rigorous, more scientifically based theories. One of them is Pomerantz's and Kubowi's theory of the principles of perceptual organization. It basically takes all the laws of Gestalt, and if you try to count all the laws of Gestalt, you go into hundreds. Okay, just try and quantify all these principles, and gets 4: it's grouping, figure-ground segregation, illusory contours and pregnance, and nesting of these. And just a demonstration. See the demonstration? Yeah. Okay. Nothing. What do you see? Nothing. We add something more and see what happens with the scene, how you perceive the scene, how you parse it into a higher level object. Okay, nothing yet. Maybe some grouping. Starting to see something. Start to see something, and then another layer of something. Okay. So this is an example of nested parsing of the scene according to these 4 reasonably simple principles. And they can be easily applied, the same principles can be easily applied to charts. Okay? So this parse is parsed by connection, by group, by proximity, and then connectivity to something. And this is the same things can be applied. I'm going to go into that, thank you. As well as other charts, everything can be applied. The other theory is Treisman's pop-out feature integration theory. Who's heard of that particular one? Pop-out effect. Yeah, heard of it. This is going to psychology studies, I presume, yes. The idea is that there are cases where you can see something pop out. This one pops out of everything else. This one pops out. There is an odd one out in here, but it takes long search. It doesn't pop out. And can you find it? Can you see that? Yeah, that's the one. And there's a difference. There's perceptually and kind of you feel the difference between something that you see immediately and something that you see when you look at things one by one. And in the 80s, when that theory was formulated, the idea was that simple things pop out, complex things don't. But and that's the theory that many study and still teach. It's unfortunately wrong. Because since then we've seen enough of evidence of complex things that pop out and simple things that don't. These things are more complex than these, and these pop out and these don't. Okay, can you see the pop out there? The other one out? Yeah, the other one out there? No, not here, not here. But the graphically very similar. That is more complex graphically. It pops out. Moreover, you can see pop out here, the other one out. Yeah. It's specifically graphically similar to the buildings. That's why they have. But it still pops out. And the difference there is not low, it's very high level. Okay? So, Ahisar and Hochstein in Jerusalem, and Ahisar was my master thesis advisor, that's why I love the theory. They improved on that idea, so taking the principle of pop-out and taking it to what it actually probably is, more correctly, is that pop-out of abstract stimuli, is whatever comes on the top of the parsing. So we start with the scene, we parse it into somehow, and whatever comes on the top pops out. And if it's not what we need, then we need to dig down and look for what we were looking for. Okay? I'll skip another one because it doesn't really matter. So, with these two in the mix, another one, we can actually say that the meaning of the chart, what we actually see in the chart, is built with the parsing of the scene, with these principles of perceptual organization, and the top parsing, the top object in the parsing, is what we see there, is the insight, and it either pops out, we can see it immediately, like this one, or it has to be looked for very slowly and laboriously. These two show the same data, okay, of rainfall by year. Okay, and here you can see easily what the driest months are. Not here. So that's our quality criterion. The quality criterion actually that comes with this theoretical mix-up is that we want the relevant information, the insights, the visual insights, to pop out. We want them to be presented in such a way, not only to be readable, not only to be readable in theory, but to be readable immediately. Okay? That would be our perfect visualization, where what we need jumps out at us, and not, that doesn't require a long search to find. Fortunately, there's a very easy way to test for that, and to have a rigorous test of visualization quality. Basically, we plot a lot of data, and we see whether the amount of data affects the time. If more data equals more time to find what we need, then it's bad. Then it's not immediate. If more data means the same time, it doesn't matter how many data points we have. Okay, 10 or 500 or 5,000, the target pops out, then we're good. It's a nice criterion, I like it. So how many time have I got left? 10 minutes, plenty. So what I did then was to try it out on 3D scatter plots. I like 3D scatter plots. I don't know why they don't work. I mean, 2D scatter plots are everywhere. They're the basic tool of exploratory visualization, not showing off, not communicating, but understanding data. The first thing you do, you plot it. And 2D scatter plots are everywhere. 3D scatter plots don't work. I was trying to understand why that is the case, and I was trying to do that with that paradigm. Basically, can you see the odd one out here? No? There is one that is odd one out. It's that blue one here, sticks out in front. That's a bit more complicated. Can you see the odd ones out in there? You can, it takes time. Compare that to this. Same scene side view. That jumps out at you, that doesn't. Okay, so that was more or less the experimental paradigm. I did 4 experiments on that. I'm not going into detail because we don't have time. But that was the general experimental paradigm, and I think it is applicable to many other novel visualization designs. And it's very simple, honestly. You just manipulate the amount of items, and you measure the time, and you see if it's flat or it's going up. And if it's flat, like that, it's good. If it's going up, it's bad. Yeah, no, see it going up. That's about. More complicated. Can you see the one out here? Yeah, that pops out. It doesn't matter how many there are. The colored one pops out. I'll make it easy for you. Can you see the one out here? Takes ages. I mean, you can do it. People did it, but that's easier. Okay, same thing from the side. Then I moved from outliers to trends. There is a trend hidden there, a 3-dimensional trend. You won't be able to see it in that resolution. Yeah, that's the trend. One of the colored points are, it's difficult, but it's much easier, it works. So to skip to the conclusion, yeah. First of all, from these series of experiments, the criterion is a simple criterion, but it works. It does distinguish between efficient and inefficient visualization for any new novel thing that you can care to throw at it. I did it since then with other things, except scatter plots. Interactivity, when we add interactivity. Well, that's specifically about scatter plots. I'm not going into there. Yeah. We have a theory, some kind of theory. It comes with a methodology that is cheap, simple, and not comparative. But specifically about 3D scatter plots, no, they don't work for outlier detection. They do work for trend detection and cluster detection quite well. And interactive 3D scatter plots are better than interactive, and that's about my findings. I think that's it for today. I kind of rushed through the experiments. I could go in detail, but then we don't have time. I would like to thank my supervisors and colleagues from Arbute. Questions?
Any cultural differences, age differences, anything like that, gender differences? Because if I compare the paradigm or your perspective to the perspective that we heard earlier from the journalists, it's two different worlds. I mean, you're working in a sterile lab, I would assume, or this work was done in a sterile lab. I know that in my lab we had to exclude once somebody who was drunk. So, and versus the journalists that you don't really know who reads the pieces, who looks at the visualizations, and how their level of graphicacy and all these other skills. So I wonder how you
well, there are two parts of this question, and the first, does the thing work? That works. And the first thing is that I made my job somewhat easier by focusing on researchers. Okay, I was trying to build a tool that will be useful to people who are trying to understand novel data. Okay. You can assume some level of graphicacy and numeracy and stuff. Second, yes, we did find some differences within the groups, within participants. That was mainly to do with their level of expertise in manipulating this kind of computer-generated 3D. So graphics designers, 3D graphic designers, and computer gamers did a much better job at manipulating this specific, at seeing these specific types of 3D patterns. And people who just used to that kind of no gender differences, no age differences, hugely. No, I mean, we did rule out colorblind participants, but other than that, there is a background effect. Yes.
Thank you. Thank you. More questions?
Copy, definitely.